This Module 6C video introduces the chemistry of alkene metathesis. I'll first begin with a section on the structure and a bit of a description of the history of alkene metathesis, which resulted in the Nobel Prize in Chemistry awarded to Yves Chauvin, Bob Grubbs, and Dick Schrock. In the 1960s, several laboratories around the world were working on alkene interchange or alkene metathesis chemistry. Chauvin was in one of these laboratories working for a French petroleum company to increase the molecular weight and the boiling points of gaseous alkenes such as propene and 1-butene into higher molecular weight liquid alkenes that might serve as precursors for petroleum, for liquid fuels. Many different mechanisms had been proposed, but in the early 1970s, Chauvin proposed a unique mechanism which subsequently was shown to explain the results that were known at that time. The Chauvin mechanism has subsequently guided the design and development of better alkene metathesis catalysts. Chauvin was working primarily with molybdenum and tungsten chloride mixtures, molybdenum and tungsten being group 6 metals. However, these initial catalysts could not be structurally characterized, and it was difficult to obtain information in support of the mechanism. Based on Chauvin's mechanism, 2 American scientists followed up on this at the beginning of their independent careers. Schrock began working with Group 4 and Group 5 transition metals, specifically titanium and tantalum. And with tantalum, Schrock was able to establish a mechanistic cycle matching Chauvin's mechanism. There was a lot of interest in developing titanium alkene metathesis catalysts. Titanium is inexpensive, non-toxic, but the Group 4 and Group 5 reagents are really reactive, very challenging to work with. Schrock eventually returned to molybdenum in the late 1980s, finding that moving from halide ligands to oxygen, nitrogen, and carbon-based ligands gave a pre-catalyst with very high reactivity, but controllable reactivity. And the structure was well understood for the Schrock pre-catalyst. Bob Grubbs also worked with titanium pre-catalysts, but decided to move toward the later transition metals and found that ruthenium pre-catalysts also conducted alkene metathesis. In the early 1990s, Grubbs reported their first ruthenium catalysts based on this structure. Originally, the ruthenium was coordinated to triphenylphosphine, but by using the saturated ring, the cyclohexane ring, tricyclohexylphosphine is more electron donating than triphenylphosphine, and that catalyst is a little bit more reactive. That is what became known as the Grubbs 1 pre-catalyst. Both the Schrock and the Grubbs pre-catalysts undergo initial reaction with alkene to give a methylene that is double bonded to a metal, which will have other ligands associated with it. This is known as a transition metal carbene, and this has been established to be the active catalyst. Moving down the page for the worksheet. The Schrock catalysts are more reactive with alkenes, but the Grubbs catalysts are less reactive with oxygen and with water. So they are practically easier to use. The Schrock catalyst includes a nitrene ligand and a carbene ligand. Both the nitrene and the carbene are formally neutral ligands, so their coordination with the metal does not affect the formal oxidation state. However, nitrenes and carbenes have only 6 valence electrons associated with the nitrogen or the carbon. As they do not fulfill the octet rule, they are highly reactive toward accepting electrons in reactivity that fills the octet for these second row elements. However, back bonding supports the stabilization of complexes of nitrenes and carbenes with transition metals. This is shown for the carbene ligands, in which the carbene non-bonded electron pair donates electrons into an empty orbital of the transition metal, and for the back bonding component, a filled d orbital of the metal donates electrons into the empty p orbital of the carbene ligand. And while it's not shown here, the same thing happens with the nitrene ligand. Turning to the second page of the worksheet, this table shows the structure of the Schrock precatalyst and the Grubbs 1 precatalyst. In this video, I'll work through formal oxidation state, the electron count, valence shell electron count for the Schrock precatalyst, and then I'll ask you to work this out on your own for practice with the Grubbs 1 catalyst. For the Schrock catalyst, we first need to determine the formal oxidation state. The carbene is a neutral 2-electron donor. The alkoxides are anionic 2-electron donors. The nitrene is a neutral 2-electron donor. Based on 2 neutral ligands and 2 anionic ligands, the formal oxidation state of molybdenum is in the +2 oxidation state. Molybdenum, being in group 6, has 60 electrons in the 0 oxidation state. In the +2 oxidation state, there are now only 4 d electrons with molybdenum. Adding up the 2-electron donation of each of the 4 ligands, in addition to the 4 d electrons from molybdenum, this is a 12-electron complex. After you work through the oxidation state electron count for the Grubbs 1 precatalyst, consider the evidence from this table to provide reasoning for the claim that the Schrock precatalyst is more reactive than the Grubbs precatalyst. And we will discuss your reasoning in class. I'll complete this first video by describing a specific example of alkene metathesis using the Grubbs 1 precatalyst. The modern catalysts are compatible with functional groups, including esters, and in most cases give very high selectivity for only the trans isomer. This concludes the first video introducing alkene metathesis.